Okay, so in this session, first I will just make a very brief point about energy consideration for pipe flows, and then we will go to the turbulent flows. So in the previous section, we drive the kind of pressure drop for a laminar flow, laminar fully developed round pipe flow. And in this session, I want to drive a general formula for a turbulent flow, which has a little bit more complexity than a laminar flow, okay? So first, let me just make a small remark or point about energy consideration for pipe flows, So velocity distribution. So far, like most of the time, in the course, we assume that velocity distributions are uniform in a pipe, right? But in reality, especially in engineering problems, we need to be more careful because velocity distribution might not be uniform, and we correct this non-uniform distribution. We correct it by introducing alpha, which is energy coefficient. So in the energy coefficient, so in the energy equation, which was again a more comprehensive form of Bernoulli equation where we derived it using energy principles, right? For internal energy, kinetic energy, and potential energy, if you remember. And it was kind of a generalization of the Bernoulli equation with by accounting for friction in fluids. So if you remember that the energy equation was P1 over gamma, and now for the kinetic energy part, instead of writing V1 square over 2, because we assume that the distribution, velocity distribution, for example, in a pipe was uniform. It was not kind of changing, right? This was what we had assumed. That, for example, if you have the velocity in a pipe, if this is a pipe, say this is a pipe, the velocity we assumed was like all like it had the V1, right? But in reality, it's not the case, right? Velocity at the edges should be 0, and then we will have something like this, right? So this is the real velocity profile. And so in order to correct this, we multiply this V1 square over 2 by alpha. So I introduce alpha 1. And then this, we write the rest of the equation plus Z1 equals to P2 over gamma plus, again, the correction factor, alpha 2 V2 square over 2 plus Z2 plus HL, which is head loss due to friction. So this is real velocity distribution, right? Okay, so this is the correction factor, just for you to remember, because we are going to use it here because we want to get a more realistic formula for especially especially in engineering applications. Okay, so now after the side note, let's go through the turbulent flows. So for turbulent flows, we want to again estimate this pressure drop. So let's review again what was the difference between a turbulent flow and a laminar flow. So when viscous effects are present, the flow might be laminar, turbulent, or in transition. Okay. So let me show this to you. What is the difference actually between these, the forms of like this laminar, turbulent, or in transition to turbulence. So if you have U here, say U is in foot per second. And here we have T, which is in second. Okay. So in a laminar flow, U is changing, U is kind of constant, is not changing, okay, with time. Especially in a, I mean, it can change, but we don't have that, the flow will be laminar if U is smaller than a particular number, okay? But then, if you, so let's say U here is up to 1 foot per second, here is up to 2, and then here is up to 3 foot per second, okay? So this corresponds to, if I want to write it in terms of Reynolds number, because Reynolds number is actually what really matters for determining the turbulence of the flow. So this is Reynolds number. So the Reynolds number, if you remember, was V, velocity, or U, I can just write it as U, times D over nu, where nu was the kinematic viscosity. So this is Reynolds number. Okay, so up to 2000, up to Reynolds number 2000, okay, the flow is kind of, we call it from 0 to 2000, the flow is laminar. Because the velocity is kind of small, but as you increase the velocity, you will see some small perturbations in the flow, okay? In a pipe, you will see some small perturbations up to, let's say, Reynolds number of 4000. Okay? And this part, we call this part as transitional. And then if you keep increasing the velocity in the pipe in time, you will see that the velocity is gonna go up and then make very large oscillations. Okay? And here where we call it, we are in a turbulent regime. And this occurs typically for Reynolds number greater than 4,000. So, and laminar flow is for typically Reynolds number less than 2,000 for a pipe flow, okay? So this was just a brief overview of what we learned and what we talked about, especially in terms of the fluctuations of the velocity which determine the turbulence of the flow. And just to note, again, turbulence is a very complicated problem. It doesn't have any analytical solution. So we typically use this kind of dimensional analysis kind of framework like Buckingham Pi Theorem to be able to get some scalings, relevant scalings in a turbulent flow. And just to let you know, the reason we have this turbulence and this nonlinearity, all of this chaos comes from the nonlinear term in the differential form of the momentum equation, which if you remember, we called it Navier-Stokes equation. And in that equation, that nonlinear term creates all this nonlinearity and all this turbulence that you might have heard in, for example, when you fly on a plane or in water, or all of these, when the flow becomes turbulent, all of these are because of those, the nonlinearity that exists in the governing equations of fluids. And Navier-Stokes equation in the turbulent form, where the Reynolds number is large, does not have any analytical solution, and even we don't know whether there exists any analytical solution for that or not. So it's not even proved that it has any analytical solution. And this is one of the open mathematics millennial open mathematics questions. It's one of the 8 open mathematics questions in the world that if you solve it, you will you can get like $1 million. So this is one of the really kind of mesmerizing open questions in mathematics. And if you're interested in fluid mechanics field, this is kind of the one of the open research field questions. And if you have any interest, you can talk to me about it, especially in pursue your kind of studies at a graduate level in this topic. So let me now get back to what we were. So I want to use dimensional analysis of pipe flows to get some understanding and kind of estimation for the losses that occur in pipes with turbulence. So we have dimensional analysis of turbulent pipe flows. So we can decompose and write the overall head loss in pipe systems as this: HL, the total equals to HL major head losses plus the head loss of minor head losses. And I want to explain what are these. So major head losses are head losses that are due to, so head loss due to viscous effects in straight pipes, and HL minor refers to head loss in various pipe components. This can be like joints, like all these different pipe components that we may have, like joints or turbines. If you have any pumps, it can also create some of those elbows. All of these can make some kind of minor head losses in this system, okay? And the major head loss is due to the viscous friction in a pipe flow. So for example, if you have a pipe, once the flow comes from the inflow and then gets out of the pipe, because of the friction at the wall, there will be some energy dissipation and therefore some energy loss, which we call it major head loss. And minor head losses again refer to those head losses due to different components, additional components in a pipe system, such as joints, elbows, and all of these kind of things, okay? So now I want to focus on major losses. So let me start it here. So for the major losses, this is again is gonna be a similar problem to the previous part, whereas with pressure drop in a turbulent flow, okay? So let's get started. Major losses. The pressure drop and head loss in a pipe depend on the wall shear stress, tau wall, right? It's very clear, because how much shear stress you have on the wall is going to be relevant and proportional to the pressure drop and head loss in the system, right? So delta P, or pressure drop, for a steady, incompressible, and not turbulent flow in a pipe is as follows. So let's review it before. So here we had a pipe where we wanted to estimate the pressure drop in a horizontal pipe with a laminar flow. And now we want to do the same thing, but with a turbulent flow, okay? So let me copy it here. So we have this, and then let me see if this is the case. Okay. So we have a pipe with radius D with length L, and then we have a, so let me copy it here because we will need this later. So we have V velocity here, velocity of the fluid. And then what else? We have, this is going to be section 1. This is section 2. And we want, what is the difference between a turbulent and laminar flow? And what else do we need to account for? Okay, so let's get a start with the writing the first thing for finding the delta P using the Buckingham Pi Theorem, and that is listing all the relevant variables. Okay, so what is this function of? So this is going to be a function of, again, the fluid velocity is going to be important in the pressure drop. The length of the pipe is going to be certainly important. The diameter of the pipe is going to be certainly important. And the viscosity of the fluid is going to be also very important, right? So these are the variables that we already had in the laminar flow, right? When we wrote the laminar flow formula, we had the same thing. And now what is distinctive about turbulence, and what else do we need to account for? So in turbulence, one more thing that is important is, if you remember, is the two more things. One is the inertia, because the inertia of the fluid is going to increase, right? So if you remember, this was the Reynolds number we had here, which was kind of important, which shows the kind of the ratio between the inertia force and viscous force. Okay, so one more thing is inertia, and for inertia I show it with rho, and rho is what? Rho is density, which is important for turbulent flow. Turbulent flows, because it kind of represents inertia. Okay, and the other important parameter in turbulent flows is what? Is something related to the pipe, and that is roughness of the pipe. And the roughness becomes important in turbulent flows because it's gonna determine the viscous layer depth that is formed in turbulent flows. So let me show it here. So here in the flow, in turbulent flows, we have like the pipe has some roughness lengths. Okay, so let me show it again. Like it can have some roughness like this. Also the same roughness here. And this is what we call and show as epsilon, which is the roughness of the pipe. And this is important. I am gonna explain it why it is important. So this is the epsilon, which is the roughness of the pipe. So roughness of the pipe is also important, because it determines the viscous layer, viscous layer depth formed in turbulent flows. In laminar flows, viscous effects are everywhere. Okay, what does this mean? Let me explain it a little bit more. So, say I have just a pipe and I just look at it from the down part of it, or just you can imagine we have a sheet, okay, anything like that, and then we have like water or air or any fluid that goes over this. So if your velocity is low, then viscous effects are going to be very important across the, say, if you can have like a channel, say, rather than a pipe. So if so let me put it here. So if your velocity is low, then these viscous effects are going to be everywhere. But if your velocity is high, what happens is if you have some, say, roughness here, let's say roughness elements here is a little bit rough, and also here, right? We don't have it's impossible to have like a perfectly smooth pipe or channel or whatever, okay? So what's gonna happen is once the flow comes here, because of this roughness, we will have a layer, kind of depending on the velocity. If the velocity is too large, the depth of this is gonna be smaller, right? We will have some region here which we call this as viscous layer. Is gonna kind of be formed here, and the rest of the flow is gonna be very turbulent. So the way the fluid is gonna go is gonna be very turbulent here because of these kind of high velocity and high inertia that it has, okay? So this roughness is very important for the depth of this viscous layer, okay? And the reason why we did not use this in a kind of in the laminar flow, and the reason was because the velocity in a laminar flow is too low. Say you can have like this is kind of a laminar flow, the velocity is too low, and when the velocity is too low, then the whole, like, if you decrease that, your viscous sublayer is going to be something like this, okay? So your whole pipe or channel is going to be, viscous effects are going to be propagated everywhere in your channel, okay? So that's why we did not look at it in a laminar flow, because viscous effects are present everywhere. But for a turbulent flow, the viscous layer is only present up to specific height, like which we call it viscous layer, okay? And the rest is we have a turbulent friction. It's not actual the viscous friction that dominates. So that's why we have these two parameters. One additional parameters that we need to take into account in writing the relevant parameters. So we need to have the inertia force, which is important for turbulent flows, and also the roughness of the pipe. These are two additional parameters that are going to be important with laminar flows. So in a nutshell, difference with laminar flows are, we have density and roughness dependence of delta P, right? These two are going to also be important for determining delta P in turbulent pipe flows. So if we use Buckingham Pi Theorem, we have now how many variables? So K is going to be 1, 2, 3, 4, 5, 6, 7. 7. So we have 7 variables. And R, which is the number of the reference variables, is 3. References. Which are M, L, T. So K minus R is going to be 7 minus 3, which equals to 4 dimensionless groups. So we can form 4 dimensionless groups in turbulent flows. So one such parameterization, and you can drive this again. So we have derived it for laminar flows, and now we have 2 more parameters. So we have now 2 more dimensionless numbers. So one such parameterization is as follows. So delta P over 1/2 rho V square equals to the phi function of what? So previously, if you remember, we only had this, right? Let me show. We only had I think we only had this L over D, right? And then on the left we had this. So another way of writing this is, so we're going to have delta P over 1/2 rho V square. So the first term I'm going to write is L over D, which we already had. And then the second dimensionless number is rho V D over mu. And the third one is epsilon over D. So these are new dimensionless numbers that come from these 2 new variables that we added. So this one is, I think by now you should recognize this. This is what? This is Reynolds number. And epsilon over D, which is the roughness over the diameter of the pipe, we call that relative roughness. So this is relative roughness of the pipe. Okay. So again, we can assume, So this comes again from the Buckingham Pi Theorem. I just summarized it. I didn't go through all the steps, but you can go through it and derive this. We can assume that the delta P is proportional to length over diameter. Okay, is linearly related to that, right? So if your L over D is larger, then your length of the pipe is larger, your pressure drop is gonna be also larger. And if the diameter of the pipe is larger, it's gonna be related the other way. The pressure drop is gonna be smaller. So we can assume this, and so I can just write down that delta P over 1/2 rho V square equals to L over D. I can just take it out, and the phi function of Reynolds number and epsilon over D. Okay? Okay. Very interesting. So this means that the pressure drop in a turbulent flow is going to be dependent on L over D, the length over the diameter, and the function which we don't know of Reynolds number and relative roughness of the pipe. So here I want to make some names. So F, I name it as friction factor. Which is delta P times D over L rho V square over L rho V square over 2. Okay, so the whole thing I'm gonna write it down as friction factor here. So the friction factor, this tells me friction factor is just a function of Reynolds number and epsilon over D. Okay. So interestingly, we found this friction factor for laminar flow. So for laminar flow, we found, what is this friction factor? Let's bring it down. We already had it here. Friction factor is 64 over Reynolds number, right? We had already defined that. So you can look at it here. Yeah, so we had derived it down here. So the friction factor is here. And then for a round pipe, the friction factor we found it is 64 over Reynolds number. So I just gonna write it down. For a laminar flow, we found that F is 64 over Reynolds number. How about turbulent flows? So for turbulent flows, we found that F is a function of Reynolds number and epsilon over D. But we don't know what it is, and this is the end of the dimensional analysis. So we just know that it's going to be a function of Reynolds number and epsilon over d, but we don't know the exact function. So how can we find this? So this can be found either from numerical solutions, or should be found a better way or more convenient way is should be found from experiments. So we can run many experiments to find the kind of dependence of this friction factor on Reynolds number and relative roughness in a pipe flow. Okay. So now I want to define the major loss. So we found this friction factor, and now I want to characterize and write the major loss based on this. And before that, I want to show the Moody chart, or let me first find the major loss, and then I want to show the Moody chart, which is actually shows the dependence of a friction factor on Reynolds number and relative roughness. Okay, so let's write mechanical energy equation between section 1 and 2. So between these two sections, I want to write this mechanical energy equation. Okay, so as you see, the elevation is the same. So let me just write it down, and then I want to make some assumptions. So P1 over gamma. And again, I have to write it to be accurate with a correction for velocity, because velocity is not necessarily uniform. So I just use this correction for velocity as alpha 1 times V1 square over 2G plus Z1 equals to P2 over gamma plus alpha 2 V2 square over 2G plus Z2 plus HL, which is major losses. Okay, so now we know that Z1 equals to Z2, and we know that D1 equals to D2. The pipe diameter is not changing here. And so this means that Q1 equals to Q2, because V1 A1 equals to A2. And also from the continuity, we know this. So, and so this is an and. I forgot to make it so. And we know Q1 equals to Q2. So this means that V1 should equal to V2. So I can write delta P, which equals to P1 minus P2, should be gamma HL, right? So these two terms are going to cancel out, and these two terms are going to also cancel out. So this means that P1 minus P2 equals to gamma HL, or equals to rho G HL. And so HL, the major loss, is going to be delta P over rho G, which is going to be what? Instead of delta P, I can write it as here. We had it, I think. Let me see. Yeah. So delta P, I can just write it as F times L rho V square over 2 over D, right? This is going to be delta P from this relation here. So let me copy it here. I have this. This is going to be delta P. And then multiplied by 1 over rho G. So rho's are going to cancel out. So you can use this from the definition of friction factor. And so HL major, this is what we found. HL major in a turbulent pipe flow is gonna be F L over D times V square over 2G. This is very important formula. So the major loss in a turbulent in a pipe flow, what you need to do is you just need to find the friction factor multiplied by the length of the pipe divided by the diameter of the pipe and multiplied by V squared, the velocity square, over 2G. Okay. So in general, for a pipe flow on a hill with V1 equals to V2 equals to V, we can write the pressure drop is going to be rho G times Z2 minus Z1 plus rho G times HL, which is the major loss, which equals to, if I factor rho G again, so it's going to be Z2 minus Z1. Instead of HL, I can just write this, major loss. So I'm going to have rho G, so, and G is going to cancel out, so I have FL over D times rho V square over 2. Okay, so this is going to be the equation for a pipe flow on a hill. If you have a hill with two Z's, this is how you can get the pressure drop. And so now I want to talk about this Moody diagram, which is how to find this friction factor. I know, like, we know for laminar flows it's going to be 64 over Reynolds number, but how about turbulent flows? And for turbulent flows, we need to do experiments. So this Moody was the first person who did these experiments to find actually what are these, what is the functional dependence. So let me write it down. The functional dependence of F friction factor on Reynolds and epsilon over D. So he investigated this through experiments, and then he created this chart, which is known as a Moody diagram. Okay, so this is one of very kind of great achievements of him that he created, and is very widely used in engineering problems. Okay, so let's see what it is. So in this axis, in the x-axis, what we have is Reynolds number. So we have Reynolds number here, which is defined as rho density times velocity times d, the diameter of the pipe. So d is diameter of the pipe, so let me write it down, diameter. And mu is viscosity, okay? And then in this axis we have frictional factor, and also here we have relative pipe roughness epsilon over d. So we want to find this friction factor as a function of Reynolds number and epsilon over d, okay? So for a laminar flow, it's pretty easy. So, and we know that the laminar flow occurs up to about 2000, right? Reynolds number 2000. If you remember it here, I just said it here. So up to Reynolds number 2000, we have a laminar flow, and after that we have a transition, and for very high Reynolds numbers, we have a turbulent flow, okay? So if you go here up to Reynolds number 2000, so this is gonna, this is also logarithmic. This is a logarithmic profile, so you need to be careful about that. So up to 2000, which is gonna be here, so this is 10 to the 3, which is gonna be 1000, and this is gonna be the second one, which is gonna be 2 times 10 to the 3, which is 2000. You see that we have this linear profile which shows the laminar flow, and it is 64 over Reynolds number. You actually don't need to use a Moody chart for a laminar flow. If you have Reynolds number, you can simply calculate it. But to make it general, Moody also plotted this laminar flow as well. And then after you increase the Reynolds number, and you increase Reynolds number by going to the right in this diagram, you have this transitional region. And then after you start to increasing it further and further, you will get to a complete turbulence, okay? So how you should find this, and these are gonna be different. So this is gonna be dependent both on the Reynolds number, as you see, and also the relative roughness. So say I have the relative roughness of different materials are also shown here. Say I have an iron cast, okay? Say I have an iron cast pipe, or let's say, which has an epsilon of 15 millimeter. And then say this is, I have the diameter of the pipe is also 1 meter. Okay, so what is going to be the epsilon over d? So epsilon over d is going to be 15 millimeter which is 10 to the minus 3 meter over 1 meter. So it's going to be 1.5 times 10 to the minus 4 is going to be the relative roughness, okay? So what I want to do, I go here. First, I want to find the relative roughness, and this is how you should find the friction factor for that, okay? So say you have this iron cast pipe with 1 meter, and then you have calculated the Reynolds number of the flow, and say the Reynolds number of the flow was 10 to the 5. Say it was 100,000, okay? And then you want to know what is, based on this, what is going to be the friction factor. You want to calculate the major losses that occur in this pipe. So the first thing you need to do is you go to the relative roughness. So what is the relative roughness? It's going to be 1.5 10 to the minus 4. So you find the closest number here. So this is 5 to 10 to the minus 4. This is 2 to 10 times 10 to the minus 4. And this is 10 to the minus 4. So it's going to be somewhere around here, right? So it's going to be somewhere around here. So I'm going to follow one of these curves. Say I want to follow this one, okay? So I will follow this. So I just color it with another color. So I follow this, and then I want to see what is my Reynolds number. So the Reynolds number is 10 to the 5. So I go here, 10 to the 5 is here in this axis. So I just draw a line, and then I find the crossing of these two lines. So what is going to be the crossing? The crossing is going to be here. And because this was also, I had this line, so it should be somewhere in between these two. So let me also plot this one. So it should be somewhere in between these two. So it's going to be somewhere here. It's approximately, so you will find it approximately. And then in order to find the friction factor, you just go to left. Okay. So this is 16, 0.016, 0.017, 0.018, and so this is going to be around 0.018.5. This is just an approximation, right? This is between what I found. And so you will get the friction factor for this problem as 0.018.5. And then once you have the friction factor, you can just plug it here and then find the HL major, the major loss in your pipe. And then you will find the pressure drop in your problem based on this major loss in the pipe. Okay, so this is the main kind of approach that you need to use in order to work with this Moody diagram, and this will be given in an exam if you need it, or another way is some simpler form of this, and one of these is what we call kind of simplifications of this Moody chart, and one of them is Haaland equation. So either we give you this chart, or another way is estimation of Moody chart equation. So you can either use that, or you can just use this estimation, which is known as 1 over square root of f equals to minus 1.8 logarithm of epsilon over d over 3.7 power 1.11 plus 6.9 over Reynolds number. So you can either use this Moody diagram, or you can use this equation, which is kind of a little bit complicated, but you are free to use any of them in the exam. So we will give any of them for you to calculate these major losses. So this is known as Haaland equation. So if you ever hear it, and this is also important formula. You don't need to remember it, but you need to learn how to use it. So please try to use both of them in your homework. Both use this Moody diagram and also this Haaland equation to be kind of comfortable with them later on. Okay, if there is any question of that. Okay, so in the next lecture, I'm going to show you and solve one example of calculating major losses, and then after that we will go through the minor losses and to the different pipe problems for single pipes, and after that multiple pipes. Okay, so in a nutshell, what we learned today is we went through the turbulent flows, and then we found these major losses for pipe flows. So we again use these dimension analysis to find the pressure drop in a turbulent pipe flow, and we had two additional parameters, variables that we accounted for, rho and E, which is the roughness of the pipe and the density of the fluid. And then we found this general formula for using dimension analysis. And then we found by defining this friction factor that the friction factor is going to be a function of Reynolds number and epsilon over D. And for laminar flows, it's just we had previously found it, which was very simple formula, F equals to 64 over Reynolds number. And for turbulent flows, we have to use this Moody diagram, or this Haaland equation, which is kind of an estimation for this Moody chart. And then the major losses is in a pipe flow in general is going to be FL over D times V square over 2G, where F is friction factor. Thank you very much, everyone.